For centuries, humans have looked to the sky to answer some of life's biggest questions, forming tales of mythology and creation to answer, how did we get here? And searching the farthest depths to answer, are we alone? Now, astronomers from all over the world use the Green Bank Telescope to find answers.
Let's take a look at the constellation of Sagittarius. Ancient civilizations created tales from the stars that form this constellation, often depicted as a centaur firing an arrow from a bow. Tonight, we can see those same stars that they viewed so long ago. The constellation's brighter stars look a bit like a teapot to me. Here's the body, and the lid, the spout, and the handle. In this area, near the center of our Milky Way galaxy, is a black hole that was discovered at this observatory in 1974. And in this area, the Omega Nebula. Let's take a closer look.
The Omega Nebula is a cloud of gas and dust in space where new stars are being formed.
While optical telescopes focus visible light waves that give us an enhanced view of the visible universe, radio telescopes provide a deeper look into the cosmos. Here, color-coded in red, we see the radio data, revealing an enormous cloud that envelops the new baby stars. Optical telescopes gather and focus light from the visible part of the electromagnetic spectrum. But visible light is just a tiny sliver of the electromagnetic energy that is radiating from cosmic objects throughout the universe. Differing only in their wavelength, scientists have developed tools to harvest different forms of light. X-ray machines help view broken bones. Sunscreen protects against ultraviolet rays that are invisible to the human eye, but can cause very visible sunburns. Infrared cameras detect sources of heat, and radio telescopes, like those in Green Bank, West Virginia, detect the longest of waves, called radio waves. Radio telescopes enable astronomers to cut through 30,000 light-years of obscuring dust and observe into stellar nurseries like the one from which our own star was born.
So I study star formation in the center of our galaxy using radio observations. There are several types of receivers that are on the GBT where we can study different types of molecules. So molecules have a specific line frequency, and so these molecules will emit at different parts of the spectrum. Looking at these spectral lines, a lot of them are excited by nearby stars that are ionizing these gas clouds that they're located in, and so the nebulas are typically where you kind of see these bright molecules.
As radio waves travel from these sources, they get fainter and fainter. By the time they reach Earth, they are barely perceptible. This is why the Green Bank Telescope, or the GBT at the Green Bank Observatory, was engineered to be the world's largest and most advanced fully steerable radio telescope. The GBT's reflector is 2.3 acres in area, the size of a college football stadium. At 485 feet, the GBT is 30 feet taller than the Great Pyramid of Giza. It weighs nearly 17 million pounds, or 42 Boeing 747s. You may think the GBT's size might make it difficult to steer. However, Green Bank operators can point the GBT to an accuracy of 1 arcsecond. That's like being able to see the individual pepperoni on a pizza from 3 miles away. The GBT regularly detects signals that are a billion times fainter than what your car radio can pick up. In fact, the telescope could easily pick up the signal from your cell phone on the planet Saturn. How does the GBT pick up such faint signals? Just like a larger bucket can collect more raindrops, a bigger dish can collect more radio waves. But it doesn't just come down to size. Green Bank Observatory engineers and machinists developed cutting-edge instrumentation, including designing and building radio detectors for the GBT. Just as your eyes detect optical light, these detectors pick up radio waves. These detectors are part of the radio receivers that are fitted at the top of the GBT to collect the faint signals that bounce off its dish. But because the instruments on the Green Bank telescope are incredibly sensitive, they are also susceptible to unwanted man-made radio signals.
Radio frequency interference, or RFI, is bursts of energy that happen to be in the radio part of the spectrum that we at the observatory are sensitive to. It can run anywhere in our frequency range from hundreds of megahertz up to hundreds of gigahertz. And so if we take a spectrum of a distant astronomical source and there's lots of RFI, you might see tiny little spikes all through that spectrum coming from cell phones, Bluetooth, or other things like that. If there's a lot of RFI, we might not be able to use those observations. And so astronomers have carefully planned for taking those radio observations, but if it's corrupted by interference, they're not going to get the science result that they expected or that they wanted. As we become more and more connected, this can be a good thing for interacting with humans out in the world, but it's not necessarily a good thing for radio telescopes.
Both the design of the GBT and its location in Green Bank help to reduce interference. The Green Bank telescope is located in the National Radio Quiet Zone. The quiet zone and surrounding mountains protect the GBT receivers against most interference. This opens up the ability to study a wide range of cosmic objects.
The research done by radio observatories, and Green Bank in particular, is important because we're probing some very fundamental questions about the universe. We know that we live in a solar system with one star and several planets orbiting around it. We're starting to know more and more that there are billions of other stars out there, and all of those probably have planets surrounding them. So with the Green Bank telescope, we can trace the processes that build those stars and then look at their evolution through time. You know, as the stars start to age and puff off material, we can trace that through radio astronomy, not just right near the sun in our galaxy, but out to the furthest reaches of our galactic home, the Milky Way.
From Green Bank, astronomer Frank Drake conducted the first modern search for a beacon from other civilizations. Now, armed with the Green Bank telescope, scientists continue this search with projects like Breakthrough Listen.
The Breakthrough Listen initiative is a 10-year, $100 million effort to conduct the most comprehensive, sensitive, and intensive search for extraterrestrial intelligence in human history. What we do in the search for extraterrestrial intelligence is we imagine that if there are other civilizations out there that perhaps have technology like ours, we might be able to detect their radio emission, the radio emission from their technology, using large radio telescopes here on Earth. The Green Bank telescope is a very important asset, a singular asset for radio astronomy, full stop, but it's especially important for the search for extraterrestrial intelligence. One of our biggest challenges in this field is telling the difference between terrestrial human radio emission and distant extraterrestrial emission. And because the GBT is located in a radio quiet zone, it makes it one of the best places to do SETI.
Researchers from around the world come to Green Bank to answer some of humanity's most intriguing questions. How did we get here? And are we alone? But it's not just researchers that benefit from the programs offered at the Green Bank Observatory. You can too. Our Science Center welcomes tens of thousands of visitors each year to learn about the invisible universe. Our specialized educational programs include Scout Merit Badge weekends, day trips, and overnight research opportunities. The Green Bank Observatory works to bring the wonders of the universe into reach, and we continue to develop groundbreaking technologies, allowing astronomers to gaze ever deeper. The Green Bank Telescope, catching the waves of the radio universe.